The distribution law. Introduction. Definition of the distribution law. It is observed that when a solid or a liquid is added to a mixture of two immiscible liquids, in both of which it is soluble, example iodine to a mixture of carbon disulfide and water, or succinate acid to a mixture of ether and water, it distributes itself between the two liquids in such a manner that the ratio of concentrations of the substance in the two liquids is always constant at constant temperature. These observations were made by Berthelot and Jung Flisk in 1872. However, it was pointed out by Nernst in 1891 that the ratio of the concentrations in is constant only when the solute has the same molecular weight, example the molecular state, in both the solvents. Hence the generalization was put in a proper form by Nernst and is called Nernst distribution law. It states as follows: a solute, solid or liquid, distributes itself between the two immiscible solvents in such a way that the ratio of the concentrations of the solute in the two solvents is constant at constant temperature, independent of the presence any other molecular species, provided that the solute has the same molecular state in both the solvents. Thus, if a solute X distributes itself between the two immiscible solvents A and B, then if X remains in the same molecular state in both the solvents, we will have concentration of X in solvent A divided by concentration of X in solvent B is equal to C1 by C2 is equal to K, a constant. The constant K is called distribution coefficient or partition coefficient. To test the validity of the law, example to verify the law experimentally, different amounts of a solution of iodine may be added to a mixture of water and carbon tetrachloride or CS2 taken in different bottles. These are then shaken and allowed to stand. A known volume of each layer is pipetted out and then titrated against hyposolution to find out the concentration of iodine. Similar experiment may be performed with other solutes and immiscible solvents. It is important to note that it is the ratio of the concentrations which matters and not the ratio of the total weights of the solute present in the two solvents. Hence, the same units of concentration must be used for each solvent. Conditions under which distribution law is valid. The distribution law is valid only if the following conditions are satisfied. First, the temperature must remain constant throughout the experiment. Second, the two liquids should be mutually immiscible. Third, the amount of the solute added should be small. Example, the solution should be dilute. This is essential because in certain cases the solute added affects the mutual solubility of the solvents. Fourth, the solute must have the same molecular state in both the solvents. Example, it should not undergo association or dissociation in any of the solvents or combination with any of the solvents. Thus, the law is not valid for the distribution of benzoic acid between water and benzene because it has been observed that in benzene, benzoic acid undergoes association to form dimers. Example, it exists as C6H5COOH whole twice. Similarly, the law is also not valid for the distribution of an electrolyte like HCl acid between water and a non-polar solvent like benzene, CS2, CCl4, etc. because the electrolytes undergo dissociation in water. Thermodynamic derivation of the distribution law. The thermodynamic derivation of the distribution law is based upon the principle that if there are two phases in equilibrium, example two immiscible solvents containing the same solute dissolved in them, The chemical potential of a substance present in them must be same in both the phases. From thermodynamics, we know that the chemical potential mu of a substance is a solution given by mu is equal to mu naught plus RT log A, where mu naught is the standard chemical potential and A is the activity of the substance or solute in the solution. Thus, for the solute in liquid A, we have mu A is equal to mu A naught plus RT log AA. Similarly, for the solute in liquid B, we have mu B is equal to mu B naught plus RT log AB. But as already stated, since the liquids A and B are in equilibrium, mu A is equal to mu B. Therefore, mu A naught plus RT log A is equal to mu B naught plus RT log AB, or RT log AA minus RT log AB is equal to mu B naught minus mu A naught. The chemical potential is defined as the partial molar free energy, the change in free energy per mole, change of composition of that component in the solution, keeping the composition of all other components constant. The activity of a substance in the solution is its effective concentration, or log AA upon AB is equal to mu B naught minus mu A naught upon RT. Further, at a given temperature, mu A naught and mu B naught are constant for given substance in the particular solvents. Hence, at constant temperature, we have from equation 4, log AA upon AB is equal to constant, and therefore AA upon AB is equal to constant. This is the exact expression for the distribution law. However, if the solutions are dilute, the activities are equal to the concentrations, so that the expression 6 is modified to Ca upon Cb is equal to constant, which is the original form of the distribution law. Change in the molecular state and distribution law. As mentioned earlier, Nernst was the first person to point out that the distribution law in the form of C1 by C2 is equal to constant is applicable only if the solute remains in the same molecular state in both the solvents. Example, it does not undergo association or dissociation in any of the solvents or combination without any of the solvents. If, however, such changes take place in any of the solvents, then the law cannot be applied to the total concentrations of the solute in the two phases, but only to the concentrations of the identical molecular species in two phases. In each of these cases, the distribution law equation is modified as discussed below for a few simple cases. Case 1. When the solute undergoes association in one of the solvents. Suppose the solute X remains in the normal molecular state in the phase 1, but N molecules of it associate to form complex molecule Xn in phase 2. Then the following two equilibria will exist simultaneously. First is X gives X, second is NX gives Xn, both are under equilibrium. Suppose the total concentration of the solute X in phase 1 is equal to C1 and the total concentration of solute X in phase 2 is equal to C2. Also suppose alpha is the degree of association of the solute in phase 2. Then concentration of the associated molecules in phase 2, example concentration of Xn is equal to 1 upon n C2 alpha, and concentrated of the unassociated or normal molecules in phase 2 is equal to 1 minus alpha C2. Applying the distribution law to equilibrium 1, we get concentration of solute X in phase 1 upon concentration of normal molecules of X in phase 2 is equal to constant. Example, C1 upon 1 minus alpha of C2 is equal to constant. This is equation number 1. Again applying the law of chemical equilibrium to equilibrium second, we get concentrated of the associated molecules in phase 2 upon concentration of normal molecules in phase 2 raised to the power n is equal to constant. Example 1 upon n C2 alpha divided by 1 minus alpha of C2 whole raised to the power n is equal to constant. This is equation number 2. Or C2 alpha upon 1 minus alpha of C2 whole raised to the power n is equal to constant. Therefore, n is constant. Taking the nth root, we get n under root C2 alpha upon 1 minus alpha of C2 is equal to constant. Dividing equation 1 by equation 2, we get C1 upon nth root of C2 alpha is equal to constant. Exact formula. When the molecules in phase 2 are almost completely associated, where alpha is equal to 1 and therefore C1 upon nth root of C2 is equal to constant, this is approx formula. Alternatively, the same result may be obtained in a simple manner as follows. Suppose concentration of the solute X in phase 1 is equal to C1. Concentration of the associated molecules in phase 2 is equal to C2 and concentration of the simple molecules in phase 3 is equal to C3. Applying the distribution law to equilibrium 1, we get C1 by C3 is equal to constant. This is equation number 3. Again applying the law of chemical equilibrium to equilibrium 2, we get C2 upon C3 raised to the power n is equal to constant. Taking the nth root of both the sides, we get nth root of C2 upon C3 is equal to constant. This is equation number 4. Dividing equation 3 by equation 4, we get C1 upon nth root of C2 is equal to constant, which is the same as derived above. Thus, in such cases, when the solute undergoes association in one of the solvents, the constant value for the partition coefficient is obtained not for the ratio C1 by C2, but for the ratio C1 upon nth root of C2. This relationship has been confirmed by studying the distribution of benzoic acid between water and benzene. The acid existed mainly as associated molecules, C6H5COOH whole twice in benzene solution. The following results were obtained. Thus, whereas the ratio C1 by C2 shows great variation, the ratio C1 upon under root C2 is nearly constant. The formula C1 upon nth root of C2 is equal to K is commonly used for finding the value of n. Example, the extent of complexity of the solute molecules in one of the solvents. This is done by finding out the concentrations C1 and C2 of the solute in the two solvents in a number of experiments. Case 2. When the solute undergoes dissociation in one of the solvents. As before, suppose the solute X dissolves in the phase 1 without any change in the molecular state but undergoes dissociation into Y, Z, etc. In the phase 2, the following two equilibria will be set. First, X gives X, second, X gives Y plus Z in phase 2, both under equilibrium. Suppose total concentration of solute X in phase 1 is equal to C1 and total concentration of solute X in phase 2 is equal to C2. Also suppose the degree of dissociation of the solute in the phase 2 is alpha. Then concentration of undissociated simple molecules in phase 2 is equal to 1 minus alpha of C2. Applying the distribution law to equilibrium 1, we get C1 upon 1 minus alpha of C2 is equal to K, which is a constant called partition coefficient. Note, it is obvious that if the solute undergoes dissociation in phase 1 with degree of dissociation is equal to alpha but remains normal in phase 2, then the formula obtained will be C1 of 1 minus alpha upon C2 is equal to K. Similarly, if the solute undergoes dissociation in both the phases with degree dissociation is equal to alpha in each, then the formula will be C1 of 1 minus alpha upon C2 of 1 minus alpha is equal to K. From the above expression, the degree of dissociation alpha can be calculated. Case 3. When the solute undergoes combination with one of the solvents. Suppose the solute X remains in the normal molecular state in phase 1, but one molecule of it combines with n molecules of the solvent S to form the compound molecules XNS in phase 2. The two following two equilibria will be established. First, X gives X in phase 1 to phase 2. Second is X plus Ns gives XNS in the same phase, both under equilibrium. Suppose concentration of the solute X normal molecules in phase 1 is equal to C1. Concentration of the normal molecules in phase 2 is equal to C2. Concentration of the solvent molecules in phase 2 is equal to Cs. Concentration of the compound molecules in phase 2 is equal to Cc. Applying the distribution law to equilibrium 1, we get C1 by C2 is equal to K, the distribution coefficient. This is equation number 5. Again applying the law of chemical equilibrium to equilibrium second, we get Cc upon C2 into Cs raised to the power n is equal to K1, equilibrium constant. This is equation number 6. Since the solvent in phase 2 is present in excess, its concentration Cs remains almost constant in spite of combination with the solute X, particularly if the solute is added in small quantity. Example, the solution is dilute, thus Cs raised to the power n is constant, and so the equation 6 becomes Cc upon C2 is equal to K1 of Cs raised to the power n is equal to K2, another constant. Adding 1 to both the sides, we get C2 plus Cc upon C2 is equal to 1 plus K2. This is equation number 7. Dividing equation 5 by equation 7, we get C1 upon C2 plus C3 is equal to K upon 1 plus K2 is equal to K3, another constant. But C2 plus Cc is the total concentration of the normal as well as the solvated molecules of the solute X in phase 2. Thus, the above equation in fact implies that total concentration of the solute X in phase 1 upon total concentration of the solute X in phase 2 is equal to constant. Hence, we conclude that when the solute enters into chemical combination with one of the solvents, there is no modification of the distribution law equation except that the numerical value of the partition constant is changed. Application of distribution law. The distribution law has been applied to the study of problems of both theoretical and practical interest, a few of which are briefly discussed below. In calculating the solubility of a solute in a solvent, when the two immiscible solvents are in contact with each other and the solute is added in such a large excess that saturated solutions are formed, then the concentrations of the solute at this stage will be equal to their solubilities. Assuming that the distribution law is applicable for such concentration, we will have C1 upon C2 is equal to S1 upon S2 is equal to K. where concentration C1 is equal to S1 is the solubility of the solute in solvent 1 and concentration C2 is equal to S2 is the solubility of the solute in solvent 2. Thus, knowing the distribution coefficient K and the solubility of the solute in one of the solvents that in the other can be calculated. In studying the extent of association or dissociation of the solute in a solvent, we have already seen that when a solute undergoes association in one of the solvents in which its total concentration is C2 and has the normal molecular state in the second solvent in which its concentration is C1, then distribution law formula is modified to C1 upon nth root of C2 is equal to K, the distribution coefficient. From this formula, the value of n can be calculated either by hit and trial method or by logarithmic method as explained below. First, hit and trial method. The values of C1 and C2 obtained in different experiments are put in the equation and C1 upon nth root of C2 is equal to K. Then putting n is equal to 2, 3, 4, etc. one by one, the values of k are calculated in each case. The number which gives constant value for k is the correct value for n. Second, logarithmic method. The formula for finding n is C1 upon nth root of C2 is equal to k, or C1 is equal to C2 raised to the power 1 upon n into k. Taking logarithm of both the sides, we get log C1 is equal to 1 upon n log C2 plus log k. For two sets of values C1, C2 and C1 dash C2 dash, we have log C1 is equal to 1 upon n log C2 plus log k. This is equation number 1, and log C1 dash is equal to 1 upon n log C2 dash plus log k. This is equation number 2. Subtracting equation 2 from equation 1, we get log C1 minus log C1 dash is equal to 1 upon n log C2 minus log C2 dash, or n is equal to log C2 minus log C2 dash upon log C1 minus log C1 dash. Hence, n can be calculated. Similarly, when a solute undergoes dissociation in one of the solvents in which its total concentration is C2 and hence the same normal molecular state in the second solvent in which its concentration is C1, then we have C1 upon C2 of 1 minus alpha is equal to K, the distribution coefficient. From this formula, the degree of dissociation alpha can be easily calculated. In predicting distribution indicators, it has been seen that iodine distributes itself between CS2 and water with the distribution coefficient equal to 400 towards CS2. Thus, if a weak solution of iodine is to be estimated, then a few drops of CS2 may be added to this solution. As a result, a considerable amount of I2 will pass into CS2 layer and give it a deep violet color. Now the solution may be titrated against hyposolution till the violet color in CS2 layer disappears. Thus iodine acts as a distribution indicator in this case. In the study of chemical equilibria leading to the formation of complex ions, example, distribution law helps us to determine the equilibrium constant for any of the above equilibrium reactions and hence to establish the formula of complex ion on the basis of the constancy and the value of the equilibrium constant. As an example, let us consider the first equilibrium reaction. The study of this equilibrium involves the following steps. First, a solution of iodine in CS2 is shaken with water to find out the distribution coefficient of iodine between water and CS2. Second, a solution of iodine in CS2 of known concentration is shaken with Ki solution, also of known concentration. Third, after the distribution of iodine is complete between the two layers, The concentration of iodine left in the CS2 layer is determined by titration against standard hyper solution. The resultant is then calculated as follows. Suppose that initial concentration of iodine in CS2 is equal to A moles per liter. Initial concentration of Ki solution is equal to B moles per liter. Concentration of I2 left in CS2 layer after distribution is equal to C2 moles per liter. Distribution coefficient of I2 between water and CS2 is equal to K. As iodine reacts with Ki, the total concentration of iodine, free plus combined, in the aqueous layer is much higher than if no Ki were present. Obviously, total concentration of I2, free plus combined, in aqueous layer is equal to initial concentration of I2 in CS2 minus concentration of I2 left in CS2 layer is equal to A minus C moles per liter. The total concentration of I2 in aqueous layer can also be found directly by titrating the aqueous layer with the standard hypo solution. Concentration of free I2 in aqueous layer can be calculated by applying distribution law. Example, concentration of free I2 in aqueous layer upon concentration of I2 in CS2 layer is equal to K distribution coefficient, but concentration of I2 in CS2 layer is equal to C moles per liter. Therefore, concentration of free I2 in aqueous layer is equal to Kc moles per liter. Therefore, amount of I2 that has combined with Ki is equal to A minus C minus Kc moles per liter is equal to T moles per liter, let's say. Now, according to the reaction, Ki plus I2 gives Ki3. Number of moles of I2 combined is equal to number of moles of Ki combined is equal to number of moles Ki3 formed. Therefore, concentration of Ki3 in the aqueous layer is equal to D moles per liter. Concentration of Ki in the aqueous layer is equal to B minus T moles per liter. Concentration of I2 in the aqueous layer is equal to Kc moles per liter. Substituting these values in the equilibrium law expression was K dash is equal to concentration of Ki3 divided by concentration of Ki into concentration of I2. The equilibrium constant K dash can be calculated. Starting with different initial concentration of iodine and Ki solutions, the value of K dash is determined in each case. A fair constancy in the value of K dash confirms the formula of the complex Ki3 or that of the complex ion I3 negative. In the process of extraction, the process of extraction is of great importance both in the laboratory and industry. In the laboratory, the process is often used for the removal of dissolved substance from an aqueous solution with the help of organic solvents like ether, chloroform, carbon tetrachloride, or benzene. In the industry, the process is used to remove the impurities from the product. Basically, the process involves shaking of the aqueous solution of the substance with an organic solvent which is immiscible with water, but in which the substance to be extracted is soluble. After shaking, the mixture is allowed to stand. Most of the substance passes into the organic layer from which the former can be separated out by distilling of the organic solvent. However, in order that the process of extraction may be more effective and efficient, the following two conditions must be fulfilled. First, the value of distribution coefficient of the substance between water and the extracting solvent should be greater in favor of the extracting solvent. It is sometimes possible to increase the distribution coefficient artificially by making the substance less soluble in the aqueous phase. This can be done by adding some substance which depresses the electrolytic dissociation of the compound being extracted. Thus, suppose that an organic acid which ionizes to a certain extent in aqueous solution is to be extracted with ether. If a strong inorganic acid, HCl etc., is added to the solution, the hydrogen ion concentration is increased and the ionization of organic acid is reduced because of common ion effect. In the solution, there will be greater amount of the undissociated acid and hence the amount extracted will be greater. Similarly, an organic base can be best extracted in the presence of a strong inorganic base. The addition of salts also usually lowers the solubility of an organic compound in water, a salting out effect, and thus increases the distribution coefficient. Second, the whole of the extracting solvent available should not be used in one lot, but it should be used in maximum number of installments. That this factor increases the efficiency of extraction can be seen as follows. Suppose X gram of the substance are present in 1 liter of the aqueous solution. Also suppose 1 liter of ether is available as the extracting solvent and that the distribution coefficient of the substance between ether and water is 2. Now, if the whole of the ether is used in one lot and X gram be the amount of substance extracted into ether, then we will have concentration in ether upon concentration in H2 is equal to X upon 1000 upon X minus X upon 1000 is equal to 2, or X is equal to 2 by 3 of X is equal to 0.67X. Thus, only 67% of the total amount will be extracted in this case. Again, suppose the whole of the ether is used in two installments, each of 500 cc. After shaking with first installment of 500 cc, suppose x1 gram of the substance passes into the ether layer. Then clearly x1 is equal to half of x is equal to 0.5x. Thus, 50% of the total amount is extracted out in this operation. Therefore, the amount of the substance left unextracted is equal to x minus half of x is equal to half of x. Now, 1 liter of the aqueous solution containing half of x gram of the substance is shaken with the remaining 500 cc of ether. Suppose the amount extracted into ether by this operation is x2 gram, then x2 is equal to 1 by 4th of x is equal to 0.25x. Example, 25% of the total substance passes into the ether layer in this operation. Therefore, total amount of substance extracted is equal to 50 plus 25 is equal to 75%. Thus, when 1 liter of ether is used in two equal installments, the percentage extraction increases from 66.7 to 75. Similarly, it can be seen that 1 liter of ether is used in 4 installments. The extraction increases further to 93.75%. A general formula can be derived which gives the amount of the substance left unextracted after definite number of operations. Suppose W gram of the substance is present in V ml of the solution made in solvent A. Also suppose that V ml of the extracting solvent P is used each time and K is the distribution coefficient of the substance between the solvents A and B. Now, if W1 gram be the amount of the substance left unextracted in solvent A after the first operation, then W1 is equal to Kv upon small v plus Kv into V. Again, after the second operation, if W2 gram be the amount of the substance left unextracted in solvent A, so that the amount extracted is W1 minus W2 gram, then W2 is equal to Kv upon V plus Kv of Kv upon V plus Kv into W. In general, after nth operation, the amount of the substance left unextracted will be Wn is equal to Kv upon V plus Kv raised to the power n W. This is equation number 3. In order that the extraction may be so efficient, clearly Wn should be smallest possible. This can be so only if the factor Kv upon V plus Kv raised to the power n is as small as possible. Now in this factor, the denominator V plus Kv is greater than the numerator Kv. Therefore, Kv upon V plus Kv is less than 1. Hence, the above factor will be smallest possible when n is the largest possible. So it follows that the multi-step extraction is more economical than the single-step extraction. Further, from the above equation, it may be seen that Wn can never be equal to 0. Howsoever large n may be, in other words, extraction can never be complete, howsoever large number of extractions may be carried out. Otherwise also, it is clear that every time the substance left distributes itself between the two solvents, some quantity, howsoever small, must be left unextracted. Note: for the purpose of numerical problems, it must be remembered that K is the distribution coefficient of the substance between the solvent A already present and the extracting solvent B. If K is given for the distribution of the substance between solvents B and A, the reciprocal of this value should be used in the above equation. The principle of multi-step extraction holds good for washing the precipitates, whereby the impurities distribute between the liquid and the precipitate. Further, in Park's process for desilverization of lead also, use is made of the principle of extraction. Silver is more soluble in zinc than in lead. Zinc is immiscible with molten lead. Thus, when zinc is added to argentiferous lead, a large quantity of silver goes into the molten zinc layer, leaving little silver in the molten lead layer. Because the distribution coefficient of silver between zinc and lead is 300 at 880 degrees Celsius, zinc containing silver forms the upper layer. Thus, by repeating the process, almost total quantity of silver can be extracted from argentiferous lead. And the determination of degree of hydrolysis. Let us first study some terms and expressions related to salt hydrolysis. Hydrolysis constant. The general equation for the hydrolysis of the salt Pa may be written as Da plus H2O under equilibrium gives Ha plus BOH. Applying the law of chemical equilibrium, concentration of products upon concentration of reactants is equal to K, the equilibrium constant. Since water is present in a very large excess in the aqueous solution, its concentration may be regarded as constant, so that we have concentration of products upon concentration of Ba is equal to K into concentration of H2O is equal to Kh, where Kh is called the hydrolysis constant. Since concentration of Ha and concentration of BH represents the molar concentration of the free acid and the free base produced, and concentration of Pa represents the molar concentration of the unhydrolyzed salt, the above expression for the hydrolysis constant may be written in a more general way as Kh is equal to concentration of free acid and concentration of free base upon concentration of unhydrolyzed salt. Degree of hydrolysis. The degree of hydrolysis of a salt is defined as the fraction or percentage of the total salt which is hydrolyzed. For example, if in a solution of aniline hydrochloride, 90% of the salt is hydrolyzed into aniline and hydrochloric acid, the degree of hydrolysis of is 0.90 or may be expressed as percentage with 90%. It is usually represented by the symbol H. Example, H is equal to number of the moles salt hydrolyzed upon total number of moles of the salt taken. Expressions for the degree of hydrolysis for solutions of different types of salt. As salts of strong acids and bases do not undergo hydrolysis, therefore to talk of KH or H of such salts is meaningless. The cases of the other types of salt are discussed below. Salts of weak acid and strong bases. It representing salt of Pa as usual, the hydrolysis may be represented as the follow. It is a case of anion hydrolysis. Suppose the original concentration of the salt in the solution is C moles per liter and H is its degree of hydrolysis at this concentration. Thus, we have A negative plus H2O under equilibrium gives OH negative plus HA. Original concentration at equilibrium is C0, 0. Molar concentration at equilibrium is C of 1 minus H, CH, CH. The hydrolysis constant KH will therefore be given by KH is equal to concentration of OH negative into concentration of HA upon concentration of A negative is equal to CH into CH upon C of 1 minus H is equal to CH square upon 1 minus H. If H is very small as compared to 1, we can take 1 minus H nearly equal to 1 so that the above expression becomes CH square nearly equal to KH or H square is equal to KH upon C or H is equal to under root KH upon C. This is equation number 1. Example, H is directly proportional to 1 under root 1 upon C. Thus, the degree of hydrolysis of a salt of a weak acid and a strong base is inversely proportional to the square root of its molar concentration. Second, salts of strong acid and weak bases. For such a salt Ba, the hydrolysis may be represented as this. It is a case of cation hydrolysis. Proceeding as in the earlier case, we get the same relationship, that is H nearly equal to under root KH upon C. This is equation number 2. Third, salt of weak acid and weak bases. Representing the salt by Ba as before, we have this. It involves both anion hydrolysis as well as cation hydrolysis. In this case, we have KH is equal to H square upon 1 minus H whole square. This is equation number 3. Here the relationship between KH and H does not involve C. Thus the degree of hydrolysis of such a salt is independent of the concentration of the solution. If H is very small in comparison to 1, we can take 1 minus H nearly equal to 1 so that equation 3 becomes KH is equal to H square where H is nearly equal to under root KH. This is equation number 4. Determination of degree of hydrolysis by the application of distribution law. Suppose it is required to determine the degree of hydrolysis of aniline hydrochloride, that is C6H5NH2HCl or C6H5NH3 positive Cl negative, which is a salt of a weak base aniline and a strong acid HCl. The method consists of two steps as follows. First, the determination of the hydrolysis constant. Aniline hydrochloride is hydrolyzed as C6H5NH3Cl plus H2O at equilibrium gives C6H5NH3 positive OH negative plus HCl gives C6H5NH2 plus H2O. The hydrolysis constant will therefore be given by KH is equal to concentration of free aniline into concentration of free HCl acid upon concentration of unhydrolyzed salt. Thus, to get the value of Kh, the aim is to find out the molar concentration of free aniline, free HCl acid, and the unhydrolyzed salt in an aqueous solution of aniline hydrochloride. This is done by shaking aqueous solution of aniline hydrochloride of known concentration with benzene. As a result, the free aniline distributes itself between the two solvents, example water and benzene, whereas the HCl acid and the unhydrolyzed salt remain in the aqueous layer. A. Calculation of concentration of free aniline in the aqueous layer. For this purpose, the concentration of aniline present in the benzene layer is found by taking a known volume of this layer, evaporating off the benzene, and finding weight of aniline left. Having known the concentration of aniline in the benzene layer, that in the aqueous layer can be calculated if the distribution coefficient of aniline between water and benzene is known, which can be found by a separate experiment. B. Calculation of concentration of free HCl produced. From the hydrolysis equation, number of moles of HCl produced is equal to total number of moles of aniline produced. But total amount of aniline produced is equal to amount of aniline present in the benzene layer plus amount of aniline present in the aqueous layer. Each of these amounts has already been calculated in step A above. Hence, the total number of moles of aniline produced and hence the free HCl produced can be calculated. Knowing the value of the aqueous layer, the concentration of free HCl in the aqueous layer can be calculated. C. Calculation of the concentration of the unhydrolyzed salt. From the hydrolysis equation, it is clear that the number of moles of the salt hydrolyzed is equal to total number of moles of the aniline produced of free HCl produced, which has already been calculated in step C above. Hence, knowing the initial number of moles of the salt taken, the number of moles of the salt left unhydrolyzed can be calculated. Further, knowing the volume of the aqueous layer, the concentration of the unhydrolyzed salt can be calculated. Alternatively, the aniline present in the benzene layer may be determined by passing HCl gas through it, so that aniline is precipitated as aniline hydrochloride. Ca- Second, calculation of the degree of hydrolysis. Knowing the hydrolysis constant Kh, the degree of hydrolysis of a solution of aniline hydrochloride having concentration C moles per liter can be calculated directly from the expression H is equal to under root Kh upon C derived earlier. Numerical problems on the determination of degree of hydrolysis. Recapitulation of formulas and units. Fast. Hydrolysis constant for Pa plus H2O at equilibrium gives Ha plus BOH is Kh is equal to concentration of free acid into concentration of free base upon concentration of unhydrolyzed salt. Second, type of salt and expression for H. A. Salt of weak acid and strong base. H is equal to under root KH upon C. B. Salt of strong acid and weak base. H is equal to under root KH upon C. C. Salt of weak acid and weak base. H is equal to under root KH. That's it. Thank you.